Hello, welcome everyone to the last but one TCS Plus talk of this term. Today we have Potechin, and the operator for today's talk is Thomas Hollenstein, and behind the scenes we have Oded Ragev, Thomas Vidic, G. Kamat, and Klemakanan. So now Thomas will go around the table, introducing all the groups.
Thank you, India. So, due to the fact that the semester almost ends or ended in many places, we have a bit of a smaller group today. We have Abhiram from Purdue, from which we have unfortunately no video signal. We have Lila Fontes from Université Paris 7. We have Piyush Piyush Srivastava from Caltech. We have a group from NYU, Shravas Rao. Thanks everyone for coming, and back to you, India.
Thanks, Thomas. So for this semester schedule, we have two Aarons left on the schedule. So today we have Aaron Potechin, and 2 weeks from now we'll have Aaron Roth. So now you know what you need to do to get good results. You can, for one of the things you can do is to change your name to Aaron. Okay, that's just one of the ways. So I see what I'm missing. Okay, and the speaker is Aaron Potechin. So he's a graduate student at MIT. So Aaron obtained his first, one of the first results I heard from Aaron was his breakthrough lower bounds and monotone switching networks, which I believe he obtained as an undergraduate. So, and the problem was left open for I don't know how many years. But today he's going to talk about sum of square lower bounds for the Planted Clique problem, and before the talk starts, so as usual, all the audience will remain muted, but you're encouraged to ask questions. Okay, Aaron, so you can start now.
Okay. Hello, everyone. My name is Aaron, and today I'll be talking about sum of squares lower bound for the Planted Clique problem. So in this talk, I'll first describe the Planted Clique problem. I'll then describe the sum of squares / Lasserre hierarchy. And then I'll describe how we analyze the Meckel-Petersen moment matrix, which is the heart of our lower bounds. Okay, so first Planted Clique. Well, let's actually start with the maximum clique problem, which asks, given a graph G, what is the largest subset of vertices which are all adjacent to each other? So it's a classical optimization problem, and in this graph here, it's the 5 vertices in the center. So how hard is Max-Clique? So it's NP hard. In fact, it made Karp's original list of NP hard problems. It's NP hard to even approximate by an almost linear factor, and it's been shown to be unconditionally hard for various models. But that's the worst case. How about the average case? Well, if we look at a random graph where we decide whether each edge is there or not with probability 1/2, the largest clique will have size roughly 2 log n, with very high probability. It's easy to find cliques of size log n, but it's open whether we can even find cliques of size 1 + epsilon times log n. Yeah, so that's the maximum clique problem. Now, how about Planted Clique? Well, in the Planted Clique problem, which was first posed by Jerem and Kucera, instead of trying to find the largest clique in a random graph, we take a random graph and plant a random clique by taking k vertices at random and adding all the edges between them. And then the question is, if we're given such a graph, for what k can we find this Planted Clique? So here in this graph, I've planted a 5 clique. Can anyone find the 5 clique?
I, C, G, H, and F.
Yep, that is the 5 clique, and I planted it by adding the red edge here. But as you can see, it's not so easy. And in fact, the best algorithm we know of to do this is from Nogalon et al., which can solve it when k is some constant times the square root of n, but not when k is smaller. And in fact, we have good reason to believe that doing better than then square root of n is hard. It's been shown that we can't do better using Monte Carlo Markov chains, the Lovász-Shriver hierarchy, or statistical algorithms. So why Planted Clique? Well, for me, it's enough that it's a very interesting problem in its own right, but it also has plenty of applications. It's a natural algorithmic problem and a good test for spectral algorithms and clustering. It's also a natural average case hardest candidate for cryptosystems, Nash equilibria, and sparse principal component analysis. Okay, now before moving on, let's rephrase the problem of whether a graph has a k-clique in terms of polynomial equations. So the idea is we'll have a variable xi for every vertex I in G. We'll want xi to be 0 if I is not in the clique. We'll want xi to be 1 if I is in the clique. And this gives us the following equations. So xi squared equals xi for all I. This forces all of the xi's to be 0 at 1. Xi times xj equals 0 if I is not adjacent to j. This forces all the ones to be a clique. And then the sum of the xi's equals k, and this says there should be k1s. So these equations are feasible precisely when the graph G contains a k-clique. Okay, so now let's talk about the sum of squares / Lasserre hierarchy. So the sum of squares / Lasserre hierarchy was developed independently by Shor, Nesterov, Frillo, and Lasserre. It's a generalization of linear and semi-definite programming. Each level gives a feasibility test on polynomial equations, which is more powerful than the last, where the rth level takes around n to the r time. These tests can often be translated into actual approximation algorithms, but their performance is not well understood. However, we do know that the sum of squares hierarchy is very powerful. It's strictly stronger than the Lovász-Shriver hierarchy and the Shirali-Adams hierarchy. It's the leading candidate for refuting Kac-Unique games conjecture. It can capture the known sub-exponential time algorithm for unique games, and it can solve many proposed gap instances for other problems. But what is the sum of squares hierarchy? Well, it took me a while to get a good intuition for it, and I like to think of it in terms of a game. So in this game, our base problem is to determine whether some system of polynomial equations is feasible over the reals. For example, let's take the equations for whether a graph has a k-clique. So in this game, there are two players, optimist and pessimist. So optimist has to claim that the answer is yes and give some evidence. Pessimist has to try and disprove optimist evidence. Pessimist wins if he or she is able to refute optimist. Otherwise, optimist wins. So now, what evidence should we ask of optimist? So the first choice is that optimist has to give the value of all the variables. But then in this case, in order to win, optimist has to fully solve the problem, which might be very hard. So at the other extreme, we can not ask optimist to give any evidence. So optimist can just say, yeah, the answer to that problem is yes. And in this case, in order for pessimist to win, pessimist has to prove that the problem is infeasible all by him or herself, which could also be very hard. And here we want something in the middle. So what we want is that for the rth level of the sum of squares hierarchy, optimist has to give the expectation values of all monomials up to degree 2r for some distribution of solutions. So that's a mouthful. Let's make it clear with an example. So let's consider the equations for whether a graph G has a triangle. So xi squared equals xi for all I. And in this case, all the edges are there, so it's just the sum of the xi's is equal to 3. So for this graph here, optimist could just point out a triangle, say x1 equals 1, x2 equals 1, x3 equals 1, and x4 equals 0. Optimist could also take each of the 4 triangles with probability 1/4. So now if we look at a given vertex xi, a given vertex, it's in the triangle with probability 3/4. So the expectation for all the xi's would be 3/4. Then each edge is going to be in the triangle with probability 1/2. So the expectation for xi, xj, when I and j are different, will be 1/2. And this here is the expected values over a distribution of solutions. However, optimists could try to lie. For example, if we ask whether this square graph here is a triangle, then the answer is clearly no, but optimists could try and give the following pseudo-expectation values, saying that every vertex is there with probability 3/4, and every edge is also there with probability 3/4. And the non-edges have to be 0. Okay, so this is clearly bogus. But how can pessimists show that this is bogus? Any ideas?
Oh, I guess if we look at it, I guess that it cannot be that the expectation of x1, x2 is 3/4 and the expectation of x2, x3 is 3/4. And at the same time, the expectation of x1, x3 is 0, because the kind of the union bound would tell that if x1, x2 appears with probability 3/4 and x2, x3 2, then x1, x3 has to appear with probability, I guess, 1/2 at least.
Okay, so that's actually, yes, I think that certainly is one way. That certainly is one way to do it. But here's two things that optimists or that pessimists can do. So, yeah, so one thing that pessimists can do is that the first thing that pessimists can do is check whether these. So I'm going to call these pseudo-expectation values because it's not actually an expectation over a distribution of solutions. So the first thing that pessimists can do is check whether these values obey the expected equations. If they do, and if they don't, then it's bogus. Well, let's check some. So we know that x1 plus x2 plus x3 plus x4 should be 3. Let's check that. So the pseudo-expectations of all of these are 3/4. And adding these up, we get 3, so that works. More subtly, if we multiply that equation by x1, we get x1 squared plus x1 x2 plus x1 x3 plus x1 x4 equals 3x1. And if we check that, well, x1 squared, that's 3/4, x1 x2, that's 3/4, x1 x3, that's 0, x1 x4, that's 3/4, so we get 9/4. And that one checks out as well. So the equations check out, but the second thing that pessimists can do is, so because we're working over the reals, any square should have non-negative value. So if we find a square which has negative pseudo-expectation value, then it's bogus. And if we check this square, then what happens is, like, the terms for the vertices are all 3/4. The terms for the non-edges are plus 0, and then the terms for the edges work out to minus 3/2 each. So we get a result of minus 3. This square is negative pseudo-expectation value, and it's bogus. Yes. And I think what you said about the triangle inequality, it can be shown using, yeah, it can be shown by checking whether a certain square has the sum of squares. It's possibly might have to go like 1 degree higher. Anyways, so in this game, we're going to restrict pessimists to those two methods. Optimist wins if he can come up with a pseudo-expectation which obeys all the required equations and it has non-negative expectation on all squares. And as a note, all these constraints on the pseudo-expectation are convex, so we can find it if it exists with semi-definite programming. And one more note. So the constraint that it should be E tilde should be non-negative on all squares. We can express in terms of the moment matrix, where P and Q are whose rows and columns are indexed by monomials of degree at most R, and the entry in row P and column Q is the pseudo expectation of P times Q. And then what happens is every function of degree at most R will correspond to a vector. Pseudo expectation of F squared will be translating F into this vector, F transpose MF. So the constraint that E tilde is non-negative on squares is satisfied if and only if our matrix is positive semi-definite. Okay, now how about pessimist? Does pessimist also have a general strategy? So the answer is yes. This is a positive Stellan-Zotz, also known as sum of squares, proof of infeasibility. So pessimist, and for positive Stellan-Zotz proof, pessimist has to find polynomials f and g of degree at most 2r, such that the following is true. So f should be equal to 0 from the problem equations. G should be a sum of squares, and -1 should equal f plus g. And if a pessimist can find f and g for which this is true, then it's clearly infeasible over the reals. And all the constraints on f and g are convex, so again, we can find f and g if they exist to a semi-definite program. Okay, so now we can see directly that optimist and pessimist can't both have a winning strategy, because if they did, well, apply E tilde to the equation -1 equals f plus g. E tilde of -1 is -1. E tilde of f is 0, because f is 0 from the problem equations, and E tilde of g is non-negative because g is a sum of squares. And it turns out by convex duality, in almost all cases, either optimist or pessimist will have a winning strategy. Okay, so now how do we use the sum of squares hierarchy? So the sum of squares hierarchy tells us approximately when our equations are feasible. As we use more and more rounds, it's harder and harder for the optimist to win. So this feasibility test becomes more accurate. Now, if in addition, so let's say we're trying to optimize some parameter k. If in addition we have a rounding algorithm which can turn a pseudo expectation into an actual solution at some cost to k, then this is going to give us an approximation algorithm. So, as a summary, here's two views of the sum of squares hierarchy. So the relaxation view is that solving our equations exactly is hard. So we've relaxed this to finding a suitable pseudo expectation, E tilde. And the key questions are, when is this relaxation feasible? And can we round from E tilde to a nearly optimal solution and get an approximation algorithm? And the proof complexity view is that the sum of squares hierarchy gives a proof system, positive Stellan-Zotz proofs, to show infeasibility. And then the key questions are, how high does R have to be to prove a given set of equations is feasible? And what can be improved to feasible with a given R? Okay, and now, how does the sum of squares hierarchy do on Planted Clique? So the essential question is, if we look at a random graph, so remember that it's high probability the largest clique has size roughly 2 log n. So the question is, if we take k a lot larger than that, for which k can optimist win the sum of squares game? So if optimist wins, then the sum of squares can't determine whether or not a clique of size k was planted, because if it was planted, optimist can win by just pointing it out. And if optimist wins anyways, then it says the same thing either way. However, if pessimist wins, then sum of squares can determine whether or not a clique of size k was planted, because if it was planted, optimist wins by pointing it out, and if not, then pessimist wins. So it distinguishes it. So for lower bounds, to show that the sum of squares does not do well at solving Planted Clique, we have to show that optimist can win this game for large k. And that means finding a pseudo expectation E tilde and the corresponding moment matrix for optimist. Okay, so previously, no non-trivial lower bounds were known for 2 or more levels. In 2013, Mecca Wigderson posted a paper claiming that R levels of the sum of squares hierarchy can only solve the Planted Clique problem when k is about square root of n. Unfortunately, there was a subtle error in the proof. So for our results, using the moment matrix, we recover a weaker version of the claimed result. In particular, the rth level of the sum of squares hierarchy can't solve the Planted Clique problem unless k is more than n to the 1 over 2r or so. And as a note, Mecca-Wigderson moment matrix is not PSD when k is much bigger than n to the 1 over r plus 1. So in order to recover the full result, if true, we have to modify their moment matrix. Okay, so now let's talk about how we analyze the Mecca-Wigderson moment matrix. Now first, what are the Mecca-Wigderson moments? So the key idea is if we let d equals 2r, and then we give each d-clique the same weight.
Aaron?
So let's, yeah?
Can you just go back one slide and tell us what this tells us about efficiency of SDP? I mean, what does it mean? What kind of running time can we expect? Is there hope to improve on the square root n?
So it's open with this. This is a lower bound. It says that like with R levels, we can't do better than n to the 1 over 2r. This is almost certainly not tight. And yeah, my guess is that like, it actually can't do much better than square root of n, but we have a long ways to go to proving that if that's true.
I see, but what the bound you prove doesn't seem much worse, right? It's just 2r instead of r.
So the bound we aim for would be 1 without the r, just 1/2 period.
Right, but compared to what Mecca and Wigderson claimed, it doesn't seem much worse, right?
It is worse because so we do have the c log n to the r squared, but the key thing is that like for small r, it's essentially the square root of n. So I think up to r is say the square root of log n. It's basically square root of
Um, but then I guess the exponent of n has an r in the new
Yeah,
result.
yeah, I missed that. Thanks. Yeah.
Yes.
And didn't they have a follow-up work recently? Just
So that's what I'm presenting. Like it's as I'm saying, it's fixing
I missed the first slide because of technical troubles. I didn't realize that. Thanks.
Yeah, that's what I'm presenting. We fix their we use that moment matrix to prove a weaker version of the claimed result. Okay, so so what are the Mecca-Wigderson moments? So the idea is we'll let D be 2R.
Aaron?
Yeah?
Can you quickly, okay, so I kind of lost it for all the discussion. Can you quickly recapitulate what we're doing now? So what we're looking at is we have a random graph, right? And we're trying to find a strategy for the optimist. So you're
yes.
And so they gave already, Mecca and Wigderson, they already presented such a strategy for the optimist by giving this moment matrix, and now you're just recapitulating this. Did I understand you right?
Yeah, so I'll now recap what the strategy is. So the things I note is just so that their strategy does prove that optimist wins when k is smaller than n to the 1 over 2r or so. However, it turns out that the strategy is not good enough when k is much bigger than n to the 1 over r plus 1. So to recover the full square root of n result, if true, optimist needs a better strategy. Okay, does that answer your question? Or should I?
Yes, sir.
Okay, I guess I'll continue then. Yes, so the Decomposition moments. The idea is we let d equals 2r and give each possible each d-clique the same weight. So precisely, let's define nd of v to be the number of d-cliques containing v. And then let's define x of v to be the product over all I and v of xi. And we set the pseudo expectation of xv to be this expression here. And this is chosen basically to make the equations work out. But here, let's not worry about it too much. Like, all we want is to estimate what the entries of our moment matrix are. So, yeah, again, our moment matrix looks like this. So technically, we should be considering all subsets of size up to R. But it turns out because of the equations, it's sufficient to consider the case when both v and w have size exactly R. So, roughly speaking, like, what are the entries of M? So, yeah, we'll be crude here and basically think of everything as constant except n and k. So the pseudo expectation of x of v, so this k choose the size of v term will be some constant times k to the size of v's power. D choose, whoops, sorry, that's technical interruption. That's better. So d choose the size of v will be a constant, ndv. So if we already have a set of vertices v, we choose d minus v more vertices to make it into a d-clique, or a possible d-clique. So that'll have size some constant times n to the d minus the size of v. And as a special case, nd of the empty set will be some constant times n to the dth power. And putting everything together, we obtain that the pseudo expectation of xv will be like some constant times k over n to the size of to the size of v. Okay, so let's give a picture for these matrices. So for the case of r equals 1, which is basically semi-definite programming, the diagonal entries will be some constant times k over n. And the off-diagonal entries will be some like either 0 or some constant times k squared over n squared, where it's non-zero if we have the edge between the row I and the column j. And I put the 2 there for scaling purposes, which we'll see later. So now for r equals 2, the matrix will look like this. The diagonal elements will either be 0 or some constant times k squared over n squared. And it'll be non-zero if, so the row index and column index are both ij. It'll be non-zero if there's an edge between I and j. So for the blue entries, where the row index and column index have one element in common, it's like ij and ik. It'll be 0 or some constant times k cubed over n cubed, and it'll be non-zero if we have the triangle. And then for the red entries, where they're totally disjoint, it's similar. It'll be 0 or some constant times k to the 4th over n to the 4th, and it'll be non-zero if we have the 4th week. So this is what the mecha weakness and moment matrix looks like. Now, okay, so there's some difficulties in analyzing it. So the first difficulty, which is not too bad, is that we only know the non-zero entries approximately. So we can fix that by separating out the discrepancy into a separate matrix and showing that with high probability its norm is small. Once we do that, now we have the non-zero entries exactly. A more serious problem is that this matrix has many zero rows and columns, which as it turns out, makes the analysis difficult. And so we fix this by filling in the zero rows and columns of our matrix. And let's call the resulting matrix M prime. Yeah, and the reason we can do that is that the original matrix is a diagonal submatrix of our new matrix. So if our new matrix is PSD, so was the original.
Aaron, can you say again, how come you can subtract delta and not worry about it?
So we'll show that it's, so I won't get into it here, but we can show that its norm is small. Like the discrepancy between like
right.
the values we expect and the actual values is small enough. It's small enough that we can ignore for this result.
But in order to ignore this, you'll have to show that M minus delta is not only PSD, but actually has no small say, eigenvalue.
Okay, yes, and in fact we will show that on the on the subspace with the non-zero rows and columns, its smallest eigenvalue is in fact very high.
And you're saying delta is also 0. Whenever M minus delta is 0, delta is also 0. So you're kind of zooming in on the concept.
Yes.
Okay, thanks.
Okay, so yeah, so we're going to fill in the zero rows of our matrix. So how should we fill in these zero rows and columns? So what we'll do is we're only going to look at the edges between the row index and column index. We'll assume that edges within the row index and edges within the column index are in a sense already present. Okay, yeah. So a more serious difficulty in analyzing this matrix is that it has many zero rows and columns, which, as it turns out, makes the analysis very difficult. So to fix this, we fill in the zero rows and columns, and let's call the resulting matrix M prime. And we can do this because our original matrix is a diagonal submatrix of our new matrix. So if our new matrix is PSD, then so is the original. So now, how should we fill in the zero rows and columns? So the idea is that we'll only look at the edges between the row index and the column index. And to do this, we'll basically assume that edges within the row index and edges within the column index are present, and just look at the edges between them. So here, in these green entries, since we are already assuming that so if it's row ij and column ij, we're already assuming that the edge between I and j is present. So all the entries now are some constant times k squared over n squared. For the blue entries, like between ij and ik, we're already assuming that the edge between I and j and the edge between I and k are present, that those edges are present. So now it's non-zero if we have the edge between j and k. And for the red edges, which are totally disjoint, it'll be non-zero if we have the four edges between ij and kl. All right, so now that we have this new matrix, let's decompose it. Let's decompose it into E plus R, where E is its expected value, and R is the random part. So we'll show that E is strongly PSD, so it has high smallest minimal eigenvalue, and we'll show that the norm of R is small. Right, so here's a picture of E. It's a very nice picture. So the green entries are some constant times k squared over n squared. The blue entries are some constant times k cubed over n cubed. And the red entries are some constant times k to the fourth over n to the fourth. So now how do we analyze E? Well, let's go back to the case of r equals 1, where we do the same thing. We have the diagonal entries. The diagonal entries are some constant times k over n. And the off-diagonal entries are some constant times k squared over n squared. Now we can write this as C2 times T2 k squared over n squared times j, where j is the R1's matrix, and some constant times the identity matrix. And then the R1's matrix is PSD. So the smallest eigenvalue of this matrix is this constant C1 k over n minus C2 k squared over n squared, which is roughly proportional to k over n. So now for our matrix, it's a similar idea. We can decompose E using something called the Jonta scheme. And the key idea is that E is a sum of PSD matrices, one of which is a constant times the identity. And so the smallest eigenvalue of E is proportional to k squared over n squared. So that's E. Now what does R look like? So the diagonal elements are 0. The blue elements, where the row index and column index have one element in common, will be plus or minus some constant times k cubed over n cubed, and it'll be positive if the edge from j to k is there. And for the red entries, it'll now be minus 1 or plus 15 times some constant times k to the fourth over n to the fourth, and it'll be positive if we have the 4 edges between ij and kl. So now, as you probably guessed, we'll decompose R into parts, like the blue part and the red part. And once we factor out the constant, we'll show that with high probability, the blue R3, the blue part, has norm the square root of n, O over root n, and the red part has norm O n to the 3, has norm roughly n to the 3 halves. So what does R3 look like? So R3 is a plus minus 1 random matrix, where the entry is positive if the corresponding edge is there. So as you can see, the structure is complicated. And to fix this, we'll partition the entries based on which elements of the row and column are equal. So here, for example, if we take the elements where the first element of the row index is equal to the first element of the column index, we get this very nice block structure. And now, so each of those blocks is just a simple plus minus one random matrix, and has norm with high probability has norm square root of O square root of n. And the idea is that we can decompose all of R3 as a constant number of pieces like the one shown, possibly having to permute rows and columns. With high probability, all the pieces have norm square root of n, or O over root n, so with high probability, the whole thing is norm O over root n. So now the red part, so here the entries will be minus 1 or plus 15, depending on whether all 4 edges are present. And these values appear because it's what makes each entry by itself have an expected value 0. So this is what R4 looks like. So I don't have time to go over here, but we can bound the norm of R4 by using the trace method, looking at traces of large powers of the matrix. And using this method, we show that the norm of R4 is O of roughly n to the 3 halves. And now we put everything together. So Yeah, recall that M prime is E plus a constant times R3 times a constant times R4. So for E we had k squared over n squared. That's its smallest minimal eigenvalue. If we look at the R3 part, the norm of R3 is O over root n. So this middle thing is going to be at most k cubed over n to the 2.5, and this will be smaller than the first part as long as n is much less than the square root of n. So that's yeah. So that part is not the main issue. The main issue is the last part, where if we plug in our bound on the norm of R4, that's n to the 3 halves. So we get roughly k to the 4th over n to the 2.5. And this is much smaller than k squared over n squared as long as k is much less than n to the 1/4. And that's why we get the n to the 1/4 there. Yeah, and this shows that if k is much smaller than n to the 1/4, m prime is positive semi-definite, and then going backwards, our original, the Becker-Wigderson moment matrix is positive semi-definite as well. Okay, so yeah, so some takeaways. So the sum of squares hierarchy gives a series of feasibility tests, each more powerful than the last, but their performance is not well understood. In order to prove lower bounds, showing that sum of squares can't solve problems well, we have to give a candidate pseudo expectation for optimist, which obeys all the problem equations and for which the resulting moment matrix is PSD. And in the case of Planted Clique, they're analyzing the Becker-Wigderson moment matrix boils down to analyzing a few relatively simple matrices related to the input graph G. Okay, so of course this work leaves several open questions. So first, can we improve the analysis on the Becker-Wigderson moments? And spoiler, if we think that the correct bound is 1 n to the 1 over r plus 1 for the Becker-Wigderson moments. Okay, but as I said earlier, our goal is to go all the way up to square root of n. So are there better moments? Is there a pseudo expectation which gives better lower bounds? And spoiler, we think that it can be improved at least for r equals 2 rounds. And of course, the big question is, can we get a lower bound roughly square root of n for more rounds? And that is wide open. Okay, so I'd like to thank Raghu for letting me use some of his slides, and I'd like to thank all of you for listening today.
Thank you.
So, Alan, I have a question. So, remember the
Yeah.
previous Becker-Wigderson paper, there was something like to analyze the eigenvalues of the PSD matrix. They were using this Johnson association scheme thing. So, is that still present? I couldn't really figure it out from the slide.
So in Becker-Wigderson's original paper, so their analysis of the expectation parts, that was fine. The problem was in looking at the random part.
And the expectation is what uses the Johnson association scheme, right?
Yeah, it's only the expectation that uses the Johnson scheme.
Okay. Okay. And what was buggy was the moment bounds on the random part.
Yeah. So, they were using matrix concentration inequalities which weren't correct. Yeah, I can't say I know. Yeah, I can't say I know what the inequalities were, what the issue was. Only that there was a bug.
Okay.
we have more questions from the audience?
Yeah, can you hear me?
Yeah, I can hear you.
I think this is a related question, but I got lost in the parameters. So your bound on the error part of the matrix, this seemed to be fine up to n to the quarter. So this is not where you have the...
But you're doing R equals 2.
Oh, that was for r equals 2. I see. So so that's the part where you lose most, is it? When you're trying to bound the norm of these of the error part, and you just get only n to the 1 over... I mean, this is where you get stuck. You get this, sorry, n to the 1 over r dependence on your bound.
Yeah, it is in analyzing the norm of the random part.
And somehow you know that this analysis is tight because you said that you know that this particular moment matrix doesn't remain PSD beyond that.
So okay, so let's see. So an argument of John Kellner shows that the Decomposition moment, the Decomposition moment matrix is not PSD when k is much more than n to the 1 over r plus 1. The result I presented here, the result I presented here does not match that. It's n to the 1 over 2r. And in order to get n to the 1 over r plus 1, a more advanced technique, analysis is needed. In the case of r equals 2, so see the paper of Montanari.
So how is there a way to phrase the problem there, that somehow this distribution that you're claiming, the way it's defined, the moments, so you're taking, you're just counting the number of cliques that contain your, this particular set of variables. So this has just too much variance, and you get stuck in claiming that there's so many large cliques or something.
So actually, the problem is that there's a specific polynomial that when you square it, it gives a negative expectation if k is too large. In a sense, the issue is that the Decomposition moments give some additional weight if you have to 2r cliques which are contained in more larger cliques. But it turns out the additional weight is, in a sense, is not enough. Let's see. I can try and present. I can try and write down John's argument on the blackboard behind me. Should I do that?
You can try, but you would have to turn off screen share first.
We're not able to see you at the moment, so I have to turn off the screen.
Well, it's okay. I don't want. Maybe there's other questions, and we can do that after, in case we have other questions.
Do we have other questions? Oh, no, it seems so. So, Thomas, do we want to take it offline or something, and or do we want? Or Alan, you can use the blackboard, and you will have to. Stop the screen share because you're not able to see.
I think we take it offline because also, unless there are more questions, because also at least it will be very hard to recognize the blackboard on YouTube.
Right. Right.
So I'd like to thank all the watchers again for watching. I'm sorry about the technical problems. If anybody has any hints on what might have caused this and how to prevent it in the future, please email me. And other than that, thanks everyone again. Next week we have Aaron Roth, and hope to see you all next week.